All right, starting up today, we have homework to actually go over and answer to. So, first question here is that we have the brightest star, R136A1, rolls off the tongue really nicely. Surface temperature, 53,000 Kelvin, and a radius of 28.8 times that of the sun. Calculate the luminosity of the star in watts. Okay, so the luminosity is the radius of the star squared times sigma times t to the fourth. Okay, so that's the formula we're going to use. However, temperature we need in Kelvin, which we have. That's 53,000. The radius, though, we need in meters. We don't have that. We have the radius is this much times that of the sun. So, to get that into meters, we're going to have that much times the radius of the sun, which this is the number that I usually use. Again, I've seen slightly different numbers around, but man, whatever, this works well enough. So the radius number that we're actually going to use is 28.8 times 6.955 times 10 to the 8. And that gives you, that's 10 to the 10. Okay. It's very tempting to just round that to 20 billion, but I'm going to do 2.003. So that's our radius of our bigger star now in meters. So now we can plug in the numbers for L. So we have 4 pi times 2.003 times 10 to the 10 squared times the constant here times the temperature, which was 53,000 to the fourth. Okay, so what are we giving? Well, we want to be squaring this times 4 times pi times 5.67 times 10 to the negative 8 times 53,000 to the fourth. To the fourth equals. Yeah, that looks about right. So we have a star and all around to here. So you should get 0.255, yeah, 5567 times 10 to the 33 watts. Okay, so that is your wattage of this star. Let's see, B, calculate the luminosity of the star in solar luminosities. So here, you're going to just take your answer and divide it by the luminosity of the sun, which is 3.28 times 10 to the 26. So divided by 3.828 and divided by 10 to the 26. We do this here. So we have a star that's about, well, 892,556 solar luminosities. So in other words, this star is 5,892,556 times brighter than the sun. So, yeah. Okay, C. If the Earth is orbiting this big star instead of the sun, same distance, how hot would it be? Okay, so we're going to be using the equilibrium temperature equation. So this equation has T star times, times the radius of the star divided by 2 times the orbital radius. So we have T EQ. Let's see the numbers we have. Temperature of the star, that is now 53,000. Times the radius of the star, which again we need to use the radius in meters. So we want 2.003 times 10 to the 10 divided by 2 times the orbital radius. And I say same distance for the Earth, so that's going to be the same. Okay, so what do we get? Let's just do divide this here. So 2 times 1.496, that gives you, yeah, 2.9. Okay. So dividing that actually is pretty simple because in fact, this is 10 to the 10 divided by 10 to the 11, so that's just 10 to the minus 1. So really all you actually need to do is just do this times 10 to the minus 1. So that would be, yeah, okay, so it's it's this divided by 10. So it's 0 66945. Okay, then we square root this. 8182. And so we'd get that the Earth would be at this temperature. 43,364.62 Kelvin. Which, if you're wondering, is that Celsius, and then times 1.8 plus 32. Okay, so you get basically 77597. So yeah, that's kind of hot, extremely hot. Yeah, that's of course definitely not happening like at all in terms of anything like life. That's right. So now D, how far away from the star must the Earth be for it to not have to have the same equilibrium temperature as it does now? So the key for this, okay, so for D here, it's the same formula, right, as the last question. But what's different is we're saying, okay, we want this number to be the same as it usually is, which is, what did I have it as? I already forgot. 278.677. Okay, so we want that to be the same as it is. Now, the temperature of the star and the radius of the star are the same as the previous question. And the radius of 0.003 times 10 to the 10. But now what we're solving for is our what is the radius of the orbit? So we got to do some finagling here. First, if we divide this by 53,000, let's do that. So 278.677 divided by 53,000 gives you that. So 0.005258. That then equals everything in this square root. Then to get rid of the square root, we got to square both sides. We got to square this, and we get that. So 2.7647. What was it? Negative 5? Negative 5. We get this lovely thing. So what we could do then is we can, if we multiply by 2RO, we can bring it up on this side and we get rid of it down here. So we end up getting 2.7647 times 10 to the negative 5. Actually, I'll just multiply by RO. So then times RO equals 2.003 times 10 to the 10 divided by 2. which I'll just do that. Well, actually, no, I'll save it. So then we can divide this. So we get RO equals 2.003 times 10 to the 10 divided by 2 times 2.7647 times 10 to the negative 5. Okay, so we want to solve for that. So we want to multiply this by 2. Okay, and then we're going to divide the radius of the star by this, which, in other words, I'm going to divide 2.003 divided by 10, and you get that really small number, but then you inverse it, so you get this number. Oh boy, okay. Not a great number to round. Let's see. 3, 6, 9, 12, 14. Okay, so this is... Okay, I'm going to actually purposely kind of round this out like a lot. So, or not round this. So you get 3.6224, 3365 times 10 to the 14 meters. That is your answer. However, I did ask for answer in AU. So to get an answer in AU, you're going to have to divide by this many meters, because that's the amount of meters in 1 AU. So you divide this, and you end up getting 2,400, I'll say 2,420. That's your answer. For comparison, Neptune is at 30 AU. So this gigantic star, in order for the Earth to be the same temperature as it is now, it'd have to be 80 times further away than Neptune. So, yeah, it's pretty far. Once you get out that far away, you just get like really tiny, far comet stuff. That's like Oort cloud territory, which we'll talk about next week. Or no, we'll talk about that Friday. So yeah, you don't get to like another star at that distance. I think if you measure the distance to Proxima Centauri, the closest star in AU, it's like 60,000 AU or something. So it's definitely nowhere near close to that, but it's ridiculously far away. For comparison, if you were actually, you know what, just to do this, because you can do Kepler's third law basically to sort of like approximate like how long the orbit would be, like how many years it would take to go. So you would cube this and then square root it. So yeah, Earth would then orbit in like 119,000 years. So yeah, just it gets completely ridiculous. But that's the point of this, to show some ridiculousness. All right, moving on to number 2. So we have the AU of all of these planets, and we're trying to find the equilibrium temperature to get these. Okay, so let's just quickly go through these. So Mercury, you're going to take the temperature of the Earth, 278.677, and divide it by the square root of the orbital radius in AU. So let's actually look that up. Let's see, do I have... I don't. Look this up. So the number you want to use generally here is the semi-major axis, so 0.387. So 0.387, square root of that, and then flip it, and we get 447 basically 448. Kelvin, and then convert to Fahrenheit. So 347 Fahrenheit. Okay, so that's quite hot. Okay, Venus is going to be 278.677 divided by square root of 0.6. Well, I'll do 723. So 0.723 square root divided by and flip it 327.74. Which in Fahrenheit 130.5. Now I'll get back to this because if you know some things about planets, you may realize something about that number, but we'll get back to that. Mars. Now that we have AU that are greater than 1, things that are further out than the Earth, we're going to get smaller numbers. So let's see, we got symmetry axis. Oh, there's the AU, okay. 1.524. Okay, so 1.524. Square root it. Oh, I hate how the equals shifts to that. And then flip it over. 225.74. Negative 53 Fahrenheit. Jupiter. What is this? Okay. Jupiter, we get, where are we? 5.2. I'll just do 5.2 because I'm lazy. 5.2. 2 square root divided by 2. 122.2 Kelvin. Negative 239 Fahrenheit, so that jumped off pretty quickly. Saturn. $9.58. So 9.58 square root divided by 278.7. 90 Kelvin. Negative 297. 8 minus 8.677. Where are we at? The 19.22. Words. 53.566. Minus 273 times 1.8 plus 32. Negative 345. And lastly, Neptune's like 30. 30.11. Yeah, okay. 30.11 square root. $50.8. Negative 368. Okay. So there you go. You can see the temperature, it does drop off quickly, but then it like there's not too much of a difference between these last four, especially like, Neptune is like, okay, the difference between Uranus and Neptune is like the distance between the Sun and Saturn, and yet the change is only like 20 degrees Fahrenheit. So you can see how it drops off very quickly, but then it sort of plateaus out. And as you might imagine, if the distance was infinity, well, then the answer would be 0 Kelvin, right? So whatever that is in Fahrenheit. But as you get larger and larger out, the difference of that gets less and less. So yeah, it does sort of stretch out as you go. Now again, these are like approximate sort of average temperatures, assuming everything was perfect, which of course it's not. And the biggest difference for all of this is Venus. Venus is way off if you look at the actual temperatures. So the answer is why. And so you might have to know a little bit about Venus to get this, but the reason is that Venus's atmosphere is incredibly thick, so its greenhouse effect is enormous. Okay, so that's the reason as to why it's so much hotter than this temperature. Because like 130 Fahrenheit, I mean, okay, that's not good, but like, that seems like, on some days that seems like it might be okay, where like you could actually go there and it wouldn't be terrible. But no, Venus is like, I don't know if we did, but maybe Russia did. But anyway, there was a probe that was sent to Venus's surface and it melted in like 15 minutes. So, this is a metallic probe thing that went through space fine, and yet Venus just murdered it. So yeah, Venus is way off. And there's other things that are off too. Mercury is a weird case where it's like off in both directions, and then I think Jupiter and Saturn are kind of off a bit, but that's more so the fact that it's hard to like, where do you measure the temperature like inside of it, so yeah. But especially for like I think Mars is actually almost exactly what it is. I think it's very close. So yeah, some of this is quite good. All right, so now we're gonna move on today to the main thing for today. And today's stuff is I'm gonna just be going through the planets, the 8 planets. There's gonna be a lot of specific numbers and specific names. You don't need to know these numbers, but I just think it's kind of neat to have them down. So, and I just think this information might be helpful to you. Or not helpful, but it's interesting. So anyway, but first though, your warm-up question: what is the definition of a planet? Now, the hint is there are 3 things. Okay, you have to say yes to these 3 questions in order for you to be considered a planet. Okay, so just think about it. One of them is pretty obvious, and the other 2. One of them is pretty obvious. The other one is not very obvious, especially how it's specifically worded. So just think about it. There's 3 things. See if you can come up with what they are. So the easy obvious one is the object must orbit the sun, or a star, I guess, if you're talking about a planet or another object, another star. But yeah, it must orbit the sun. Okay, moon, not a planet because it orbits the Earth, not the sun. So yeah, that's the easy one. The second one, and you might have kind of thought about this, and but maybe not sure you probably don't know the exact word for it. But well, the object must be spherical. Okay, roughly spherical. Again, none of the planets are perfect spheres. Some of them are very close. I think Venus is actually very, very close to being a perfect sphere. But like, if you look at a picture of Saturn, so here, let me actually go back to the thing for Saturn. You'll notice, especially for Saturn and Jupiter, are most obvious, but they're not like spheres. Like you might not be able to tell this way, but trust me, if you look at this image and like turn your head sideways, like 90 degrees, you'll very obviously notice that is not a perfect sphere. It bulges in the middle. Okay, so that's something that happens because the planets are spinning. They sort of bulge out of the equator and they're kind of squished in at the poles. So that's true for all planets, but it's most obvious in Saturn and Jupiter, just for a couple reasons. One of which is that they're made of gas, so gas is, more easily moved than rock, but it does happen. So yeah. But anyway, they're not like random shapes, right? They're at least spherical-ish. Now, the technical term for this is something called that they're in hydrostatic equilibrium. Okay, fancy term, but basically it's a spherical object. In other words, you have a thing that because of its own gravity, it sort of compressed itself into a sphere. And you have to be a certain size in order to do that. Okay, so this excludes like asteroids, for example, right? Asteroids are not spherical; they're sort of random shapes, but they orbit the sun, so that's why those are not considered planets, because they're not in what's considered hydrostatic equilibrium. Now, the moon again is in hydrostatic equilibrium; it is a sphere, but it doesn't orbit the sun, so it's not a planet. So yeah. Now the third one is the tricky one. And a lot of people, this is the main one that comes down to why is Pluto not a planet, because Pluto orbits the sun and Pluto is a sphere. So seems to fall under that banner well enough. And most people think, oh, it's a size thing, right? It's actually not. Okay, so it's not a size thing. It's not because Pluto's too small. The third rule is that the object must have a cleared orbit. Okay, so what this means is that there's no other planet-like object that's in its way. Okay, all of the planets, again, Earth, it orbits around fine, there's nothing in its way. Jupiter, there's nothing in its way that's going to cause any problems. Pluto, there's stuff in its way. Okay, there are other Pluto-like things that are all kind of around in that same area, and they all get in each other's ways. They're not going to collide, but like their orbits do cross each other. They just end up so they don't. They're never going to cross each other like at the same time. But there's a bunch of those things, and those are considered dwarf planets. So if you have something that does orbit the sun and it is spherical, it's in hydrostatic equilibrium, but it's not in a clear orbit, it's considered a dwarf planet. So theoretically, I guess you could have something that's like Neptune size that doesn't have a cleared orbit and therefore wouldn't be a planet. But the thing is, once you get to something that is like big enough, just over millions of years, your gravity will end up clearing your orbit anyway, right? So it is sort of related to size, but it's not like, oh, because it's like less than, I don't know, 100,000 square meters, like it's not a planet. There's not like it's not a strict cutoff like that. So that's kind of the whole thing with size. So these are your three definitions of a planet, and with these three terms, there are 8 objects in the solar system that agree to these terms: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. There are a bunch of other dwarf planets that follow the first 2 terms besides Pluto. There are technically only 5 official ones, but there's a bunch more that are like basically official. They're just not considered official for some reason. I don't know why. They fulfill all the requirements for dwarf planets, and we even have like names for them that aren't just like serial numbers. So yeah, if you count the ones with serial numbers, there's like 1,000 dwarf planets. Okay, so this is like ridiculous. So that's kind of the issue, where it's like, well, either we remove Pluto and we have 8 planets, or we have like 1,000 planets. Yeah, so that's kind of the whole issue with that and how that argument came to be. So let's start with the closest to the sun and go out from there, starting with Mercury. I already typed all this up because I didn't want to have to type this out. This would take forever to type this out. I actually mostly just copied and pasted this from something from a couple years ago, but they still had to add some information. So Mercury is the smallest of the planets. Here's its mass and radius numbers. Again, these are both compared to the Earth. Again, you don't need to memorize these or anything like that. But it's about 5% the mass of the Earth, a little bit more than a third of the size of the Earth. So it's pretty small. It's roughly, it's a bit bigger than the Moon. It's pretty similar to the Moon, though, in terms of like its look and composition and stuff like that. But that said, there are other moons around other planets, at least one, maybe 2, I don't remember, that are actually bigger than Mercury. So that's the thing that's kind of interesting. But again, they're not planets because they orbit other planets and not the sun. Its surface gravity is, again, that's your G's. So if you remember, we talked about gravity. So that's compared to the Earth. So it's 38% of the Earth's gravity. There's its density. You don't have to worry about this. Basically, Mercury is the second most dense planet. So it's the most. So that's why, even though it is like the smallest, its gravity is actually like pretty close to Mars's, even though Mars is noticeably bigger, but Mars is less dense. So that's kind of a thing with that. So because Mercury has a lot of metals in it that are like fairly, heavier metal kind of elements and stuff. So it's very dense. Its orbital distance, again, that many AU. There's a lot of 0.38 on here. It's kind of interesting. So again, we've seen that. And now here's the orbital period. So it takes about 88 Earth days, so for Mercury to go around the sun. Now the very interesting thing is its rotation period, 58.646 Earth days. Now, what this means, and again, this is basically how long it takes. This is the thing is, I would normally say this is what a day is like, but that's not true, because this is how long it takes for the Mercury to turn around 360 degrees. But in the time that it takes to do this, it's already like, it's already orbited the sun a good amount. So even, let's say, I wish I could, you know what, let me try to draw this out. Paint, because who cares? Okay, so brush, yeah, that's fine. Okay, let me get a bigger one. Okay, so if here's the sun, right? Here's Mercury, and let's say it's facing that way. Okay, now in the time it takes to turn all the way around, it's going to end up like here. Okay, but then it's facing that way again. So you see that like while it's orbiting around, it's turning around like in a really, so for example, when it's up, let's see. Oh god, it's going to be difficult to figure out. Okay, so that's like, it's in quarters basically. So I want it like, see, that's like halfway. Then here, not great. Okay, so this is, so at this point, it's facing this way. At this point, it's facing this way. At this point, facing this way. So like, you can see that if you were standing on the surface of Mercury here during like this entire time, like this, you're at night basically. But then once you get to here, let's see, then now it's daytime. You're facing this way. Again, once you get back to this position, now you're facing this way. And then we got back to this position. Now you're facing this way. Back to this position. Now you're facing that way. See, now it's still day during like all of this. Let's see, and then you get to here, and now it's starting to not be day, and then you get to here, and now it's night again, and then like you see what I mean? It's the actual like day-night cycle is really confusing and complicated. And in fact, there was something like if you were to stand on the surface of Mercury and just stare upward, the sun would like seem to go backwards and forwards throughout the sky because of how the relationship between the slow spin of Mercury and its orbit. Actually, really interestingly, the orbit of Mercury in its rotation. So here, something I want to show you. So 58.646 times 3 divided by 2, it's basically the orbit. So Mercury is something called a 3-2 resonance. I'm not going to get into orbital resonance because it's very complicated in terms of like what exactly happens and how it works. But planets often sort of like line up in these sort of patterns, and this is one of them. So that basically Mercury turns around 3 times every 2 times it goes around the sun, and that's sort of very interesting. And so it's very interesting how that works in terms of how sunrise and sunset works. And again, sometimes it looks like the sun is like reversing direction in the sky if you're on Mercury. It's very complicated, but it's kind of an interesting thing if you want to look into it. So yeah. Average temperature. So this is sort of something that you might think is weird. It's like, okay, so 152 Fahrenheit, that's actually like, I guess it's not terrible. But then again, when we did over here, 347 Fahrenheit. And I said that one's actually, and I said there was a weird thing about that. So how does that work? So the thing with this is that Mercury has like no atmosphere. Okay, it technically has one, but functionally it has no atmosphere. So what this means is that there's no heat circulation. So the day side of Mercury is stupidly hot. Okay, like 500, 600 degrees Fahrenheit hot. While as the night side of Mercury is stupidly cold, like negative 300 degrees Fahrenheit. Okay, there's no circulation of heat at all. So that's why the average is kind of like a not terrible number, because it's super hot and super cold. So the average is like, well, kind of hot. So yeah, talking about average temperature in Mercury is kind of pointless. It's better to say average day, average versus average night. That gives you a lot more insight into that, but I just want to keep it consistent with how that works. So yeah. Average day, average night temperatures. Again, average day is like 600, 700 degrees Fahrenheit, while average night is like negative 200, negative 300 Fahrenheit. So it's big difference with that. So yeah, Mercury, it's Basically, it's like if you took the moon, made it a bit bigger, and stuck it right next to the sun, and it orbits. Well, it orbits quickly, but it rotates slowly. And it has a lot of like metals in it, and the temperature's all weird. And yeah, there's Mercury. Mercury's kind of strange, but there you go. Also, Mercury does not have any moons, which kind of makes sense. I mean, it's a very small planet, so having a moon is kind of like expected, or not having a moon, especially since it's the closest to the sun. So if there was something that would like maybe fall into Mercury's orbit, it'd probably just end up falling into the sun anyway, right? So yeah, it makes sense that Mercury probably wouldn't have a moon. Next up, though, we have Venus. Now Venus is closest to Earth in size, right? So it's 95% the radius of Earth, a bit smaller in terms of mass. Gravity 90%, so pretty close to Earth. The density, it's a little bit smaller than Mercury. Yeah, 5.2 to 5.4. But still, you know, it's a rocky planet. It's not that far off. Orbital distance, again, it's 72%. So, you know, not terrible. Now this is... hold on. Okay. Orbital periods, so again, Mercury orbits the sun in 88 days, Earth days. Venus orbits the sun in 225 Earth days. And I think that's like... Let me double check. 225, is it... the 4-3 resonance? No. I don't know. Whatever. Doesn't matter. Is it... Who cares? Doesn't matter. Okay. But yeah, so it orbits at about that range. How that works there. So, nothing too surprising. Here's the super weird thing, though. Its rotation period is 243 Earth days. So what this means is that it takes 18 Earth days longer for Venus to just turn around than to go all the way around the sun. So what this means is a Venus day is longer than a Venus year. And that's super weird. And the weirdest thing about it is that it spins in the other direction. Okay, every single planet, for example, if you were to go above the North Pole of the Earth and stare down at it, it would be spinning counterclockwise. Okay, that's the direction the Earth would be spinning. Mercury, same thing. Great, it's a lot slower because it's, you know, not 24 hours, it's 58 days, but it's in the same direction. The sun actually is also spinning in that direction as well. Venus is spinning in the opposite direction. And so you could describe this in a couple ways. You could say either its orbit is like reversed, or some people like to say that its axis, you know, like the Earth's axis is tilted a bit. It's like 23 degrees or something. It's not straight up. Some people say Venus's axis is like 170 something degrees. It's like it's almost like its North Pole is on the bottom almost. It's sort of a semantics argument. Like, what are you talking about? But yeah, so if you are on Venus, the sun would rise in the west and set in the east. Also incredibly slowly. Because of how this whole rotation works. It's super weird, but that's what happens. And this sort of a joke in astronomy stuff is that if we don't know why something is the way it is, that people just say, I don't know, because something hit it. So why is Venus so slow and spinning the other direction? I don't know, something hit it. Like, that's sort of the idea. Nobody knows. Like, it's super strange, and there's not really a good reasoning behind that. And this is where you get to the temperature being very, very off. So again, I mentioned the equilibrium temperature says Venus should be like, 130 degrees. No, it's like 800 degrees. Venus is hotter than Mercury on average. And that's because of the greenhouse effect. Its atmosphere is carbon dioxide, sulfur, I think, or sulfur dioxide. It's a lot of that. It's very thick. If you look at a picture of Venus, you definitely see that is all atmosphere. Okay, you don't really, you don't see the surface of Venus. And I think actually is there an atmospheric pressure thing on here? Let's see. Yeah, see how like it says axial tilt 177 degrees, right? It's saying to the orbit. It's almost saying, it's saying it's like almost flip all the way over. That's the argument for that. But let's see, atmosphere. Yeah, surface pressure. Okay, so 91 atmospheres. So if you were standing on the surface of Venus, the air pressure would be 91 times stronger than the Earth's atmosphere. Okay, so that's ridiculous in terms of its pressure. See, here's like kind of the surface of Venus, what it would look like, but we can't see the surface because it just has a stupidly thick atmosphere of what? Let's see. 96% carbon dioxide, sulfur dioxide, and all this other stuff. But yeah, the carbon dioxide is by far, again, Earth's atmosphere is like 0.1% carbon dioxide, and like I think it's actually less than that. And like that's what people are worried about, and we should be worried about. I'm not diminishing this, but just think about I think it's because we're like what 450 parts per million, right? So that's like that's less than 0.1. It's like 0.04%. Anyway, so like that is a problem in terms of like habitability. Not 96%. That's a little bit more of a problem, right? So you can see how because of that it just gets ridiculous in terms of how hot the freaking planet is. And this is why you get things like the probe that melted. So, yeah, Venus is stupidly hot. It also does not have any moons. This one may be a little bit... Mercury, it seems... Okay, that makes sense why there wouldn't be any moons. Venus, maybe... I don't know. But especially if you compare it to Earth. But this is sort of why we think Earth is a bit of a special case. And I think I've talked about this before, but I'll get into more detail in a little bit. But yeah, Venus does not have any moons. So, there you go. So, Venus... close to Earth in terms of size and gravity and stuff like that, but it has a very slow day that's also in the opposite direction, and it's stupidly hot because of its really thick atmosphere. All right, Earth, these numbers are going to be kind of boring. Hey, what's the mass of the Earth? Oh, it's 1 times the mass of the Earth. What's the radius of the Earth? Oh, 1 times the radius of the Earth. Surface gravity, 1g. Density, okay, that's an actual number. So here, yeah, Earth is actually the most dense planet, which is kind of interesting. It's very close to Mercury, right? Earth is 5.5, Mercury was 5.4, but it is actually the most dense, which is kind of interesting. And then we have, orbital distance, 1 AU. Here's your orbital period, 365.256, this keeps going, but this is the whole thing about, why we have leap years and why. So the rule for leap years, what is it? It's every 4 years is leap year, unless it's every 100 years, in which there's no leap year, unless there's every 400 years where there is a leap year. Okay, so 1900, no leap year. 2000, there was a leap year. 2100, there will not be a leap year. Okay, and so that's the schedule for that. And I think it was something like, if we stick to that, our calendar will be off by 1 day in like 60,000 years or something. So like, it's pretty good, right? So yeah, that's what we did with that and kind of have an issue with that. And here's something you might be surprised at. The rotation period. You think, 24 hours. It's not. It's 23 hours, 56 minutes, and 4 seconds. And you might think, well, huh? What? Why? Right? That's like off by a good amount. Like, that's not even close. I mean, it's kind of close, but like not really. Like, that seems kind of bad. And so here's why. It actually is related to this thing that I explained about for Mercury. So let me sort of get rid of everything. Okay, that's actually fine for now. So we have, let's see, at this point, the Earth, it's facing this way from the sun. Now, I'm going to do an exaggerated example of this, but the Earth takes 23 hours and 56 minutes to turn all the way around. But when it's done that, it has moved on in its orbit. So, but the thing is, think about it in terms of day, right? At this point, the sun is on the exact opposite side of the Earth. If you were standing here again, the sun is now not the exact opposite side of the Earth, right? That would be sort of like that way. Again, I'm over-exaggerating this. So that extra 4 minutes, basically, to get to 24 hours is because of this discrepancy. Basically, you turn all the way around, and then you have to turn a little bit more just to get to where, basically, you're, because of the fact that you moved to go through that. So this is what is known, actually, the rotation period. It's known as a sidereal period. Basically, it's just literally how long have you turned around 360 degrees versus how long have you actually turned so that the sun is in the same place in the sky. So the fact that the sun is in the same place in the sky, that is almost exactly 24 hours, kind of by definition. It's technically not exactly 24 hours because of stuff, but it basically is. It's much closer than this is, by the way. But yeah, so this, technically also for Venus and Mercury, this is also the same thing I was talking about. Again, it takes 243 Earth days for Venus to turn all the way around. That does not mean in 243 days the sun will be in the same place in the sky. Again, same with Mercury, and I explained that because of the orbit, it's much more exaggerated. But this is sort of a small instance of that, where it still does affect it a little bit, but yeah. So that's sort of the gist of that. Average temperature, again, we talked about that, 59 Fahrenheit as of now, though it seems that will increase at least a little bit. But yeah. And then we have one moon, which is Moon. Now, this is, our moon we think is kind of special, because it's a large moon. I think it's the 5th largest moon of all of them in the solar system. It's not the biggest, but I think it's the 5th or 6th. And it is definitely the biggest compared to its planet. Okay, so all of the other moons are orbiting like Jupiter and Saturn that are much bigger planets. So it seems kind of weird that like, why do we have a moon that's as big as it is compared to our planet? Because again, Venus, closest in size to the Earth, it has no moon at all, not even a tiny one, right? Whereas we have this really big moon. And so this gets to the idea, this is one of the reasons, again, there's other like geological reasons, where people think that our moon was actually created in a collision, where we think a Mars-like object hit the Earth during the very early parts of the solar system, and part of it, during that collision, a lot of it broke off, and we ended up with that forming into the moon. So that's something that's interesting about the moon that we think. So if anything, it seems likely that planets that are about our size probably would not have a moon, or they would have maybe a really tiny one that doesn't really do anything. So, and some people argue that the fact that we have a large moon that actually gives us like tides and stuff like that is actually very important to life. So that's an interesting thing to think about. We don't know how actual effective it is, but that's an interesting thing to theorize. You'll also notice that, you may not notice this for now, but this, where I have it written as moon, that is bolded. I have done that specifically because when we get to talking about more moons, I've bolded the names of the moons that are spherical. They are in hydrostatic equilibrium. Okay, the moon is in hydrostatic equilibrium, it's spherical, and that sort of separates it from most other moons, because most other moons are not spherical. The ones that you know about are, because they're bigger and we know about them, but, most of them are not. So, yeah. Makes it kind of special. Okay, moving on to Mars. Mars is about 1/10 the mass of Earth. It's about half the size of Earth. Surface gravity is 0.37. That's actually smaller than Mercury, isn't it? Yes, it's a little bit smaller than Mercury. So even though Mercury is noticeably smaller than Mars, like 0.55, this is 0.38. Mercury actually has a larger... it has a larger surface gravity, because, and here's the thing, the density of Mars is kind of weirdly small for a rocky planet, right? It's still greater than all the gas planets, but again, compare all the others. This is 5.5, Mercury is 5.4, Venus is 5.2, this is 3.9, so it's a noticeably less dense planet, which is kind of interesting. So yeah, that's just kind of a unique thing about Mars, that it's not very dense, and also why its gravity is noticeably less. Again, 1.5 times the distance from the Earth. It orbits at about 1.88 Earth years, so whatever the month-day conversion is for that, I don't remember. And its rotation period is actually pretty close to the Earth, so it's about 24.5 hours. So, and again, like Earth, it does rotate in the same direction. Venus is the only one that rotates in the opposite direction, so it takes a little bit longer than the Earth to rotate, but it's not like a weird thing like Mercury or Venus or anything like that. So, yeah. Average temperature, pretty cold. Negative 82 Fahrenheit. It's not exactly the nicest temperature. That said, there is a good amount of range, and part of the range is because the atmosphere is very thin. I think it's like 1% of the Earth's density of the atmosphere. So because the atmosphere is very thin, it doesn't spread out the heat very well. So it can get to like 70 degrees, like positive 70 degrees Fahrenheit on Mars. It can also get to like negative like 150 degrees Fahrenheit on Mars. So there's a good amount of variation. It's not quite as extreme as Mercury because it does have at least a bit of an atmosphere. And again, it's also, since it's not as close to the sun, it doesn't get like, sheared away on the day side. But yeah, there's a good amount of range there. And so what's interesting is that water ice is almost always like actually ice, right? You can actually, because you think, well, the temperature, if it gets to like 70 degrees, it could melt. Yeah, but we haven't witnessed that happening as far as I know. But we do see Mars having like ice caps that like grow and shrink with the seasons. So you're thinking like, wait a minute. But what's happening is it's dry ice. So the carbon dioxide is getting frozen out of the atmosphere when it gets cold enough. So it's kind of interesting how, just like how our ice, we have ice and snow that grows in the winter and, and shrinks in the summer. Mars is the same thing, but it's dry ice instead because it's colder. So yeah. There are signs that liquid water used to be on Mars, and I think I've talked about this before, that we think that there was liquid water on Mars, but because Mars is smaller, its core cooled quicker, and that turned off its magnetic field, which meant its atmosphere was able to be stripped away by the solar wind, and then because of less atmosphere, it couldn't. The greenhouse effect went down. In Mars's case, it actually did not want to cool down, and it ended up having its oceans turning into ice, or because it's either turning into ice because the temperature went down, or actually evaporating because the pressure went down. So yeah, that's sort of the thing about that. But there's evidence of water used to be on Mars because there's a lot of like well, they're called canals, but they're not. That makes it sound man-made. They're not. And stuff like that we can see. So yeah, a lot of evidence of that. That's interesting. Mars does have 2 moons. They're both very small. Okay, so very small. They're not spherical. Phobos and Deimos. I'm not sure about the names of those actually come from. They're probably some Greek deity that's related to Mars. Oh, I should mention the names of these. So the names of all the planets, well, asterisk on that, but we'll get to that in a second, are named after Roman gods. Again, Earth obviously is the exception. So Mercury is the Roman equivalent of Hermes, which is the Greek messenger. This whole thing is he zooms around, and that's the whole point, is Mercury moves quickly through the sky. Venus is Aphrodite, supposed to be, goddess of beauty and all that kind of stuff. Of course, and so one of the things is that Venus, all of the formations on Venus in terms of mountains and craters and valleys and all that kind of stuff are named after women, which you could also argue like, oh great, you gave the women the planet that's literally just on fire and just melts things and is completely inhospitable, so hooray inclusivity, but whatever. So yeah, and then Mars is the Roman equivalent of Ares, god of war, so that's so there's probably Phobos and Deimos, I'm sure, are related to that in some way, but I'm not sure what they are. But yeah, they're 2 tiny moons. There is, if you may know, there's an asteroid belt between Mars and Jupiter. There's a bunch of asteroids. It's most likely that Phobos and Deimos were just part of the asteroid belt, but they just got a bit too close to Mars. So that's kind of why you have, hey, why do you have this really small planet like Mars that has moons, but like Venus has none? That's probably why, because of the asteroid belt. So yeah, and I believe actually Phobos, was it Phobos? I think it was Phobos, where it's actually slowly getting closer to Mars, and in a few million years, we think that it will actually it won't collide with Mars as like a normal hit, but it'll actually break apart because of the gravity of Mars will be strong enough to literally split it apart, and then those pieces will impact Mars. But yeah, so that's in a few million years, so I don't think you can wait for that one. All right, moving on to Jupiter. Jupiter is the Roman name for Zeus. Okay, Big Daddy Zeus, who is, your ruler of the gods, the big boy in the sky. Over 300 times the mass of the Earth, over 10 times the size of the Earth. Surface gravity, surface gravity, there isn't really a surface on Jupiter, because it's a gas planet, 2.5 times. Density is, again, way less because it's gas. And it has an orbit of about 5 times that of the Earth, and it orbits in about 11.8 years. So that's how long it takes to go around. And interestingly, though, its rotation is less than 10 hours. So even though Jupiter is a giant planet, it's the biggest planet, it turns all the way around in like 10 hours. And this is partly why I said that Jupiter and Saturn, you can see the fact they're not spherical, that they kind of bulge out in the middle a lot more easily, because since they spin really fast, the effect is more obvious. So you can see it with Jupiter. Saturn's the easiest one to see, partly, I think, because it's less dense, so it's easier for it to show off. But Jupiter actually is the fastest planet in terms of its rotation. So yeah, it spins really, really quickly, which is kind of surprising. So Jupiter, again, it's made of gas. The different layers, because you look at a picture of Jupiter. Right, let me pull a picture of Jupiter. You see all these different layers, right? These different bands, a white layer, kind of brown layer, kind of yellow layer, all that kind of stuff there. And we think what happens is because it's spinning around so fast, basically the different types of gases are sort of segmented into like different regions. And then, of course, you have the Great Red Spot, which you may have heard of, which is this like gigantic hurricane-like thing that is like 3 times the size of the Earth. So that's fun. Let's see, what is the atmosphere made of? Okay. Yeah, hydrogen, helium. Okay, that's fairly. And then methane, ammonia, hydrogen deuteride. That's deuterium, actually. Ethane, a little bit of water vapor. Some ammonia ice, water ice, ammonium hydrosulfide ice. So a lot of weird stuff in here. Now, what we think is there's a thing. Oh, let me try to find. An image of this, because here's what we think is going on in the inside of Jupiter. It's very interesting. Yes, we have, of course, like your atmosphere, your Jupiter atmosphere. hard to see. That's really hard to see. Where we think that you have, like, it's mostly hydrogen, but as you go in, the hydrogen sort of, like, translates because of the insane pressure as you get further in, and of course it gets hotter as you go further in. It, like, becomes this weird metallic hydrogen that has, like, super strange properties, and you sort of have, like, a metal hydrogen that's... So it's very weird, and this idea of this metallic hydrogen is sort of like, what is the actual core of Jupiter? What even is that? We don't really know. Oh, that's a moon. Whoops. So it's very strange in terms of what we think about this, and it's not really well understood. Because, again, we just don't really know how this stuff works when your pressure is, like, hundreds of thousands of times more than the Earth. So, yeah, we don't really know how that works. But you get to some very interesting stuff from that there. Let's see, what else do we have? Okay, the average temperature. Again, this is sort of not, like, the most kind of accurate in terms of understanding how this works, because it depends on where you are, right? On the very if you're on the very edge of Jupiter, you're going to be colder than if you go further in. As you go into the atmosphere, it gets warmer, right? Because it starts trapping heat. And if you get into, like, the center of Jupiter, it's probably, like, stupidly hot, probably more than Venus. But, and again, there's no really good place to say, oh, this is where it is. So I think this temperature was, like, how hot it is in Jupiter if you are low enough so that the atmospheric pressure is the same as Earth's atmosphere. Okay, so, yeah, it's kind of an arbitrary point to say what that is, but you can kind of see that works. Now, Jupiter, as you may see, has 79 moons, and the thing is, this number is increasing all the time, because when I originally created this list, and this was just only a couple years ago, the number was like 71, okay? So we are finding moons around Jupiter all the time. Now, and I have listed all of them. Now, I have ordered these in terms of when they were discovered. So, yeah, and you'll see there are some of these that also don't have, like, actual names. They have, like, kind of code names. How this works, so S stands for satellite. That's sort of a natural satellite, is sort of the definition of a moon. And then this is the year that it was discovered. J is noting that it's around Jupiter, and 19 is, like, the number of them that were found in that year. So all of these, I mean, besides the very first ones, probably, all the more recent ones, they even, you know, oh, Euclide, like, it didn't used to have that name. It probably used to be named, I don't know, S2003 J7. I don't know, right? You know what I mean? So it's all different depending on how that works. And I don't know why, like, you know, oh, S2003 J2 got a name, but S2 did not get a name, but S2003 J3, because I don't see that, did not get a name, or did get a name. It's one of these. You know, I don't know the process behind that or how that works, but that's how this all goes. Yeah, so we have, and again, you can see here, you can definitely see the bolding here. So these four moons, Ganymede, Callisto, Io, and Europa, are in hydrostatic equilibrium. They are spherical. Ganymede is the largest moon that we have seen. Well, it is the largest moon in the solar system. It's bigger than Mercury. I know it's bigger than Mercury. I'm not sure if there's the second biggest is bigger than Mercury, but Ganymede is definitely bigger than Mercury. So it's the biggest moon. I think Callisto's the third biggest. I don't remember. I have to go look at this again. But yeah, Ganymede, Callisto, Io, and Europa. These four moons were seen by Galileo, okay, back in the 1600s. So you can actually see these four moons with a fairly not great telescope if you're looking at Jupiter. So you can actually notice them. Then you have all these other moons, and all of the moons of Jupiter are actually named after lovers or descendants of Zeus. So you can see, hence, you know, or Jupiter in this case. So, you know, he was a busy man and got around a lot because he couldn't keep it in his toga. So yeah, there's a lot of them. I'm not sure to pronounce all these. So I don't know if I want to go through, but yeah, Ganymede, Callisto, Io, and Europa, and then Amalthea, Himalaya, Elara, Pasiphae, Sinope, Carme, Lysithea, Ananke, Leda, Themisto, Thebe, Metis, Adrastea, Caleroe, I don't know, Praxidike. I think it's the A is always like pronounced, not like a it's not like the English silent E thing. So Megaclite, Iocaste, Calike. Oh, I can go. I'm not gonna do the whole thing. But yeah, there's a lot of them. And again, there's definitely some that we don't have names for yet, so they'll come up with some name at some point, I guess. I don't know. But yeah, the vast majority of these are all just like random. They look like asteroids, basically. And I mean, that makes sense. Again, Jupiter's very close to the asteroid belt, and it's also freaking huge, so it makes sense it would catch a lot of random rocks flying around. But yeah, Ganymede, Callisto, Io, and Europa are the main big ones that are actually, you know, spherical and are important. So yeah. right, moving down to Saturn, we have, it's not quite as big as Jupiter. It's 95 times the mass of the Earth, and it's about 9 times the size. Gravity is actually, like, kind of small, which is kind of weird. It's only about, but again, this is the surface, quote-unquote, gravity of Saturn, so it's not really meaningful. Saturn is the least dense planet. It's the only one that's less than 1, which means that Saturn is less dense than water. So water has density of 1 gram per centimeter cubed. So if you were to theoretically have enough water, you know, water that was bigger than Saturn, and you put Saturn onto it, Saturn would float on the water. So that's interesting. But yeah, and this is also partly why I think the bulging is very obvious, because it's not very dense. It's about 9.5 times as far away as the Earth is. It takes almost 30 years to go around. But again, its rotation is very quick. Jupiter's faster at, what was it? A little bit less than 10 hours. Saturn is about 10.5 hours. So it does take a little bit longer to rotate, but that's still very, very fast. Average temperature, again, similar to Jupiter, this is like a little bit inside of the atmosphere, but still, you know, negative 218 degrees. It's not exactly very pleasant. And there's 82 moons around Saturn, so way more, no, not way more, but even more than Jupiter that we found. There are more, though, that we have seen that are spherical. So Titan is the big one. Titan is the second biggest moon in the solar system after Ganymede. Again, I'm not sure if Titan is bigger than Mercury, but it's very close if it's not. But then we also have Iapetus, Rhea, Tethys, Dione, Mimas, and Enceladus. Those are all spherical moons orbiting Saturn. Mimas is, I think, the smallest spherical moon spherical object, basically, that we see in the solar system. It's also the one that looks like the Death Star. If you've... Here, let me get an image of it. There. See, it's got this big, giant crater thing that looks weird. So, yeah. It's the smallest astronomical body that is known to still be rounded in shape because of self-gravitation. So, it's actually not in hypostasis. That's weird. Well, I don't know the specifics of that. But yeah, basically, it's the smallest spherical object. So, yeah. But then you get all these other ones, Hyperion, Phoebe, Janus, Prometheus, blah, blah, blah. Those are all not spherical. Now, Saturn actually... Okay, so Saturn, interestingly, because most of the planets, probably people kind of know what their equivalent is. Saturn's is the Roman equivalent of Kronos. In Greek, which is the Titan of like time or something. So Saturn's actually a Titan. So all of the names of Saturn's moons are based off of Greek and Roman Titans, except they sort of ran out of those. So they ended up sort of borrowing names. Let's see, there's Inuit, and there's some Norse in here as well. For example, I know Fenrir is one of them. Where is it? There it is. Fenrir, Surtur, some other ones too that I just don't recognize off the top of my head. But yes, I know. Oh, probably Sotungur, Thrymr, Ymir. Those are all definitely Norse. But yeah, some of them are Inuit. Oh, and there was something else too. I don't remember. But yeah, so you kind of got a bunch of names. So how this works here. So Saturn's moons are kind of an interesting mix of stuff, but they're Norse, Inuit, Greek and Roman Titans, all that kind of stuff. So all that's really in there. And again, there's a ton of them that still have code names. One thing that's interesting is that apparently I looked in that, like, because you think, wait a minute, because I had these ordered by like when they were discovered. So like, wait, then why is the 2009 one like in front of the 2004, all these 2004 ones? So I noticed, and I looked on when I look at Wikipedia, and all these 2004 ones, they were all like listed as discovered in 2019. So my guess is that like we had some signals from like telescopes and stuff that were from 2004 where people looked at them and were like, maybe that's a moon, but I don't know. And then now it's more like that only in last year that they actually like couldn't confirm, yes, these are moons. So that's my guess, but I don't know. So yeah, there you go. There's your Saturn. All right. Next up, skip this space for some reason. The planet that everyone makes fun of was his name. Now, I'm going to be technical here. This is based off... The actual name for this derives from Uranus. So, you should say, like, Uranus or Uranus or whatever is, like, the more accurate thing. So, between Uranus and Uranus, Uranus is the more accurate way. It's not just people saying it because, we don't want to say anus. No, that is technically how it should be said. But, like, yeah. I'm going to complain about this name in a little bit, though, so I'll come back to this. Mass, again, it's about 14.5 times mass of the Earth. It's a little bit less than 4 times the radius. Surface gravity is actually a little bit less than the Earth. Density is more than Saturn, but not much. It's about 19 AU away. Takes 84 years to go around. It rotates in about 17 hours. Now, Uranus is the one where it's rotating on its side. Okay, so instead of spinning like a top or whatever, it sort of rolls like a wheel. Now it doesn't follow the orbit around, if that makes any sense. So how do I explain this? It's very hard to explain this without like having something physically to show you. But okay, so think of like the pole of Uranus as like that's the axle of the wheel, right? That's where it's turning. The axle itself doesn't like move with the orbit. Okay, so it's not like the North Pole, for example, is always facing the sun. That doesn't happen. So it is sort of, it's rolling, but it is sort of facing in the same direction as it moves around. I don't know if I'm saying this very well. Maybe you can find like an image that shows the orbit, or like a GIF that shows the orbit of Uranus. It's interesting how this works. And again, just like with Venus, where we're like, its orbit's in the wrong direction, and also it's like upside down. That's why, because something hit it. That's the guess for Uranus, because I don't know, something hit it. I did actually see another thing that was an idea that maybe it actually like was originally like from some other solar system and just like was a rogue planet and just came in to ended up orbiting the sun. That seems unlikely, but like that's would be an idea as to why it's sort of oriented wrong. So I don't know. But yeah, that's something interesting about that. Average temperature, again, getting very cold, negative 300 Fahrenheit. And there's 27 moons. Now, again, we have these moons that are all, these are the ones that are in hydrostatic equilibrium, the spherical-ish ones: Titania, Oberon, Ariel, Umbriel, and Miranda. And you may notice that, like, hey, a lot of these like sound like actual names and not like weird, you know, god things. I mean, we have like Francisco and like Belinda and Bianca and even Juliet, and you're like, wait a minute. For some reason, I don't know why, all of Uranus's moons are named after characters in Shakespeare plays. I don't know why, but they are. So yeah. That's how they're named. I don't know who, well, I mean, IAU decided that, but I don't know why they decided that. So, but they did, so there you go. Yeah, I don't really know what the deal is with that. Okay, so, and I did say, though, speaking of names, I was going to come back to the name. So, I said earlier how all of the planets are named after Roman gods. That's not true. Uranus is not Roman. It's the Greek one. I don't know why. So, for some reason, someone decided that they were going to name this planet the Greek one, where all the rest are Roman, and they named it the Greek one, where the name is now made fun of because it sounds like anus. So, like, they should have just named it the Roman one, which actually sounds fine. The Roman equivalent for Uranus is Caelus. Or is it Keyless? I'm not sure how to pronounce it, but it's this, okay? So, because I've heard AE is often says like an E sound, so it's Keyless, Caelus. Either of those sound fine. I think Caelus sounds better, but whatever. So, like, come on. You can't... Who decided that was something? Also, there's a whole weird story about the naming of Uranus and how, like, it was first discovered by a dude, and the rule was that, like, in, like, the 1700s, and the rule was that, well, if you discovered it, you could name it, and, like, he wanted to suck up to King George of Britain, so he literally was going to name Uranus, like, King George, or something. He was just like, what? So, and everyone else was like, no, that's dumb. But he was like, no, but I want to do it. And everyone's just like, ugh. So there's a whole weird story about that if you want to look into it. But it's still dumb that that's what ended up happening. So, anyway, that's what we got with that there. But moving on to the last planet, Neptune. So Neptune, also gas planet like Uranus. It's actually very similar to Uranus. It's a little bit more massive, so 17 times the mass of the Earth versus Uranus is 14, but it's a little bit smaller, so 3.8 compared to 3.9. So very similar, but a little bit different. So its gravity is a little bit more. Again, density is a little bit more, 1.6 compared to 1.2. 30 AU, takes 164 years to go around. And it also rotates a little bit faster. Yeah, faster. So 16 hours compared to about 17 hours. So, yeah, interesting that the gas planets all rotate faster than the Earth. So, interesting to think about why that would be the case. Both Uranus and Neptune are sometimes referred to as ice giants, not gas giants, because even though there is gas in the upper layers, we think that because it's so cold, a lot of their interior is sort of like ice particles that aren't, like solid objects, but sort of floating around in like in the void. So there's sort of technicalities with that and exactly how they work and all that kind of stuff is very, very complicated. You can look into that more if you're interested. Let's see, average temperature, of course, you have very cold, negative 330. Again, very close to Uranus, actually, which makes sense as you get very far out there. Then the differences in temperature sort of stop mattering a lot. There's 14 moons around Neptune, so less than Uranus. And we have, again, Triton. That's the one that is spherical. One of the ideas, actually, because I think Triton orbits, again, it depends on the thing, but a lot of the moons, most of the moons, orbit. I said that like all the planets, if you look at them from the North Pole, except Venus, and again, Uranus is tilted, but they all rotate counterclockwise. The planets also all move counterclockwise around the sun, and almost all the moons move counterclockwise around their planets. Not all of them. There's a lot of the small ones that actually don't, but especially the big ones do. But Triton doesn't. So Triton actually does orbit the other way around. It orbits clockwise. And so this is one of the ideas that Triton was maybe like another Pluto-like dwarf planet that actually ended up being caught by Neptune. So that's an idea as to why that's the case there. But yeah, then we have all these other things. Neptune is named as the Roman equivalent of Poseidon. So all of these planets are named, or all of the moons are named after like aquatic deities and creatures and stuff in Greek and Roman mythology. So that's kind of what the thing is for all of that. Yeah, and that kind of gets to the end of that. So, and I think that gets to the end. Yes, it does. So, this is probably super long. But, I don't know, I just think a lot of this info is kind of interesting, even if you don't need to know the exact numbers of everything, but whatever. I just realized that I remember seeing this was off, and I thought, oh, it's not a big deal, probably they're all like that, but then that one wasn't, so, yeah, okay. Anyway. So, your wrap-up question is, I want you to list the planets from their shortest day length to their longest. Okay, you don't have to remember the numbers, but you'd just be curious to kind of put that in there and see what you can remember from that. So go ahead and put that in, and then come back when you're done. Okay, so shortest day length is actually Jupiter. The largest planet has the shortest day length of about, a little bit less than 10 hours. Second shortest is Saturn, which is like 10.5 hours. Next is Neptune at 16 hours. Then Uranus at 17 hours. Then we have Earth at 24 hours. Mars at 24.5 hours. Then we jump rather considerably to Mercury at like 50-something days. And then to Venus at like 240 freaking days. So that's the order from shortest to longest. Again, it's kind of similar to like biggest to smallest, interestingly, but not quite. Actually, the only thing that's... all of these are in order of mass except Venus. That's interesting. So anyway, the big question as to why that would be the case. If anything, you would think that the smaller ones would be quicker and the biggest one would be slower, but that seems to be the opposite. So yeah, interesting how that could all work. So your homework assignment is a little bit of a longer one. I want you to write a small essay. Okay, so think of like a few paragraphs, think like half a page to full page over a regular piece of paper, about one of the planets that we have here, one of these 8. And I want you to sort of research info on your own. So again, don't just parrot what I said here. Get more into like the composition and some interesting things about them that's beyond this. Think of this as, again, like a mini research essay, but again, mini, right? I don't want you to go crazy on this. I mean, if you really want to, okay, fine, but you don't have to. To get sort of the info that you want from this. Now, I'm not leaving it completely up to random chance, so I have a list, which you can see in the form, that will say who everyone writes in. Unfortunately, the list is like really awkwardly formatted, but that's just because for some reason the Google form like doesn't let me like space things out by pressing enter. Like there's no line breaks for some reason on the Google Forms when I'm writing a question, which is dumb, but I just spaced out the way it is. So hopefully it's a little bit more manageable. So I've split you up roughly equally. I just started like with period 1 and just went through last name and then sort of period 2 and blah, blah, blah. So yeah. So you got kind of a random planet assigned to see what you can get and come up with something with that. So something pretty small, nothing super crazy. But just get some info in there that you might think would be interesting. So yeah, think of it as like, hey, I am assigned to tell someone about this planet. Here's some interesting stuff about it. There you go. Nothing crazy, but that's what you got. Okay, I'm afraid to see how long this is, but that's what we got with this. random planet information with me. So there you go. Okay, I'm done.